When when we were talking about the card problem, when we were drawing two cards and draw those with replacement, what we saw was, even though, like say, what's the probability that we draw hearts on both, hearts on the first and hearts on the second. Even though we know that, yeah, when I do the probability that it's hearts on the first, it's 13 out of 52. And then for the second one, the probability that it's hearts on the second one, well, we base it on the condition that the first one happened, but since it's with replacement, does it change this probability at all? No, it doesn't change it at all. It's still 13 out of 52 because we're doing it with replacement. And so this this probability, we're doing the probability that it's hearts on the second, but it didn't change because there was a hearts on the first, even though we're going under that assumption. We found out last time we need to do that. It doesn't change here because we're doing it with replacement. Well, in that case, that's what's known, these events here, the hearts on the first, hearts on the second, those are known as independent events. Independent events. And the definition, if you will, definition is independent events are events for which the occurrence of one doesn't change the probability of the other. So this is events for which the occurrence of one doesn't change the probability of the other. And that's what happened in this particular case. Down here. So in this particular case, even though this probability, we say, yeah, this is the probability that it's heads given that heads on the first occur, it didn't change it. It's still 13 out of 52 because we did it with replacement, right? If it was without replacement, this would have changed. But since it's with replacement, these are known as what are independent events. And what we're going to do with that is, if A and B are independent, okay, so let me first of all write the so again, the general and probability formula, the probability of A and B is probability of A times the probability of B, but it's conditional probability of B given A. If A and B are independent, then probability of A and B can just simply be written probability of A times probability of B. And so, not a real big change, but the slight change here is, notice the second one is not a conditional probability because, I mean, you can still put it there, however, B is not affected by A and A is not affected by B. That's the gist of it, okay? And so it just, really what it means is you can just start multiplying their probabilities for an AND probability. Okay, and so let me give you a couple of examples here. So if it's just an independent, if the events are independent, for example, let's say there's a 40% chance of selecting a green ball, jar, container, whatever. If the selections are independent, so if we see that word, and we don't have to worry about conditional, but anyway, if the selections are independent, okay, what, number one, what is the probability of selecting 3 green? What is the probability of selecting 3 green? If all the selections are independent, it's probability of selecting 3 green. Well, again, the word and is not here, but it's understood here, and again, sometimes writing it out is helpful. So what this means is I want a green on the first, one way to write it, and green on the second, and green on the third. Isn't that what that means? This is what this means. Okay, now, since they're all independent, okay, so I would do then the probability that it's green on the first, 40%, 0.40. If we convert it over to a decimal. What about green on the second? Well, since they're independent, green on the second has the same probability, even though we've gone with green on the first. Same probability, still 0.40. And then green on the third, guess what? 0.40. And so that and there again, that's another reason. And means multiply. So we're going to multiply 0.4 times 0.4 times 0.4, whatever that gives you. I think it's about 0.604, something like that. Does that sound right? You gonna check me on that? .064. All right? Is everybody okay? Make sense? All right, one more on this one, then we'll do another example. But all right, so that's the probability of selecting 3 green. What's the probability? What's the probability if we select 3? Again, none of them were green. So again, we're selecting 3, but none of them were green. Well, again, that's not green on the first, not green on the second, not green on the third. However you want to write it, think about it. But it's, all of them are not green. So what's the probability that the first one's not green? Well, there's a 40% chance of getting green. So what does that leave to be not green? 60%? Yeah, 60%, 100% minus 40 are not green. Right? So the probability that it's not green on the first is 60% or 0.60. What about not green on the second? Well, again, it's independent, and so that 0.60 is going to stay 0.60. There's no change in the probability. And then not green on the third, 0.60. So this case, you got 0.60 times itself 3 times, which gives you 20.2, or about a 21%, 21.6% chance. Is that okay? Question or concern? Well, let's do this one. also as an example here. Okay, so in a large city, probability of catching a burglar is 30%. All right, so again, we'll do 3. If a detective is assigned 3 cases independent of each other, there's our, which just means, again, you don't have to worry about the conditional thing now. So 3 cases independent of each other. Find a couple of things here. Find the following. Number 1. Let's just, all right, so number 1, find the probability that the first one's caught, and the other 2 are not. So we're catching the first one, but not the other 2. Well, what does that mean? Again, catching the first one, so call it C, we're caught the first one, and then we're not going to catch the second one, and then we're not going to catch the third. Isn't that what that means? All right? Catch the first one, but not the second one, not the third one. Well, there's a 30% chance of catching the first one, so we're going to say, we're talking about the probabilities here, so the probability of catching the first one is 30%, 0.30. What about then the second one? Well, the second one we're going to do the probability of not catching it, so yeah, that's our set. What's left out of 100, I guess you might say, 70%. So probability of catching is 30%. Therefore, probability of not catching the burglar is 70%. So that's what we're talking about for that second one there. It's 0.70. And then the third one, probability of that, not catching, well, they're all independent. And so again, it's not going to change any. It's still going to be 70%. Not catching is the probability of that. So it's just 0.30 points. And again, the word is and. Kind of why I wrote it out there. So that and means multiply. And means multiply. And so those are the 3 we would multiply there. So it's the same basic idea as the other one. I get 0.147. Is that okay with you? All right. Now let me show you one more that has another little twist to it. Finish this off here. All right, so number 2 on this one. What's the probability that exactly 2 are caught? So I don't have a specific order there. It just says I'm going to catch exactly 2 of them. Catch 1, 2, 3. So let's think about that. So how could I catch exactly 2 of them? There are several ways. A couple of ways anyway. Okay, so I could catch the first one, and then catch the second one, and then not catch the, because I want exactly 2 of them caught. So catch first, catch second, and then not catch the third one. there, okay? And so that would be the point 30, right, yeah, point 30, and then 0.7. And then those three multiplied together. Give me 0.063. But that's not the only way to do this. Because, all right, so that's one possibility. Or there's another way to do this. I could do catch the first, but not the second one, and then the third one. That'd be a different scenario. All right? So I've caught two of them, but it's a little different than the first one. Now, good thing is here, 0.30, 0.70, 0.30 would be the probabilities there. They're all independent. So it's the same three, but a little different order, but they still come out to be 0.063. Is there any other way I could do this? There is another way, isn't there? The first one could not be caught, so not catch the first one, but then catch the other two. So catch 2, catch 3. Right? So that'd be a little different. As far as the numbers go, though, I mean, it's a different order, but when you multiply them, you still get the same thing. But it is a different probability, if you will. They're all 0.063. And I wrote this word or up here for a reason, because I can do it this way, or this way, or this way. So the and here means multiplies. What does the or typically mean? Remember what we said or typically means? Or means add. So we're going to add these three together. 0.063 plus 0.063 plus 0.063. And that'll give us our total here. So sometimes you might have to break it up, and they won't necessarily all be the same, but this one is, this scenario is. Is that okay? Any cause for concern there? You got that one?